Okay, Assalamualaikum and good day. Okay, I will continue my lecture for chapter 3, part 2A, which will cover about short circuit analysis. Okay, this is the outline for chapter 3, part 2. Okay, for part 2, I will divide into 2. Okay, this one is for A. Okay, A part. Okay, and these 3 will cover in part B. Okay, this is the diagram types of current. Okay, we have here is normal current and overload current and also short circuit current. Okay, this one will be analysed in part 2. And lastly is ground fault current. Okay, I will explain about the current in the next slide. Okay, first we go to normal current. Okay, normal or load current may be defined as the current specifically designed to be drawn by load under normal operating condition. This one is under normal operating condition. Okay, normal motor current varies from low values. Okay, this one under light loading to medium values under medium loading to maximum values under maximum loading. Okay, this one is for normal motor. Okay, normal current flow only in the normal circuit path. Okay, without any fault. Okay, the normal circuit path include the phase and neutral conductor. Okay, it does not include equipment grounding conductor. Okay, next we go to overload current. Overload current is greater in magnitude than full load current and flows only in the normal circuit path. Okay, it is commonly caused by overload equipment, single phasing or low line voltage, and thus is considered to be an abnormal current because the current is in overload condition. Okay, some overload current such as motor starting current or lock rotor current are only temporary. Okay, overload current is greater in magnitude than full load amps but less than lock rotor amps. Okay, next is short circuit current. Okay, short circuit current is greater than lock rotor current and may range upward of thousands of amps. Okay, so very high value, high amps. Okay, the maximum value is limited by the maximum short circuit current available on the system at a fault point. Okay, so means that the short circuit current occur when there are fault happen in the system. Okay, short circuit current may be further classified as bolted or arcing. Okay, large amount of short circuit current will flow into a bolted fault than the arcing fault. Okay, next, ground fault current. Okay, ground fault current consists of any current flow outside the normal circuit path. Okay, that is ground fault current. Okay, ground fault current flow in equipment grounding conductor for low voltage system. Okay, but in medium and high voltage, ground fault current may return to the source through the fault. Okay, this one is for medium and high voltage. Okay, ground fault current on low voltage system may be classified as leakage, bolted or arcing. This one is for low voltage system. Okay, next, source of short circuit current. Okay, there are 4 sources. The first one is the synchronous generator. Okay, when a short circuit occurs downstream of a synchronous generator, it may continue to produce output voltage and current. Second one is synchronous motor. Deliver short circuit current into a fault until the motor completely stops. And then the third one is induction motor. Short circuit current decays very quickly. And lastly is supply transformer. Okay, transformer impedance will also limit the amount of short circuit current from the utility generators. Okay, this is the waveform of the source of short circuit current. We can see here that the wave, okay, is decay from the zero axis. The value must be decay. Same goes induction motor. Okay, the value still decay. And for synchronous motor also we can see that there are decay for the waveform. Okay, this symmetrical and asymmetrical fault current waveform. We can see here for totally symmetrical current. Okay, we can see that the positive side and the negative side is almost same. Okay, so all the value for positive and negative is same. Okay, for totally asymmetrical current, this one, okay, totally different value. So we can see here positive value, positive side, and the negative side is totally asymmetrical. So totally different of current value. Okay, for partially asymmetrical current here, okay, we can see this one is asymmetrical, but this one is symmetrical. Okay, and then this one is symmetrical, and this one is also asymmetrical with positive value. So partially asymmetrical. Okay, this is the explanation of symmetrical and asymmetrical fault current. Okay, symmetrical and asymmetrical are terms used to describe the symmetry of the short circuit current waveform around zero axis. Okay, if the short circuit occurs in an inductive reactive circuit at the peak of the voltage waveform, the resulting short circuit current will be totally symmetrical. Okay, if the short circuit in the same circuit occurs at zero of the voltage waveform, the resulting short circuit current will be totally asymmetrical. Okay, the symmetrical short circuit current consists only a pure AC component. This one is for symmetrical. Okay, but for asymmetrical short circuit current is the actual current that flow during a fault condition. Okay, so it consists of DC and AC component that contribute to a certain amount of DC offset in the waveform immediately after the initiation of the fault. The amount of DC offset or asymmetry depends on the point when the fault occurs. Okay, the instantaneous peak, okay, short circuit current is the maximum peak instantaneous fault current on the symmetrical short circuit current waveform. It is a function of XR ratio of the system. Okay, we can see here from this waveform, you can see there are three parts. The first one is the instantaneous peak short circuit current, the highest value. Okay, and then here is the asymmetrical short circuit current. Okay, because the waveform is not asymmetry. And then the third one is the symmetrical short circuit current. The value is consistent, same. Okay, this is the line to neutral equivalent circuit. We can see here when the fault occur here, okay, current will flow in the circuit as this formula. Okay, this is the fault current flow to the circuit, and then from this equation, this formula, we can get what is the IRMS by using this formula. Okay, IRMS is equal to Vm divided by square root 2 divided by Zs, and we also can get theta, okay, which is equal to this formula, inverse tangent x divided by r, and also we can get the zs, which is equal to this formula. Okay, next we go to first half cycle asymmetrical fault current. Okay, we can see here this is the formula for first half cycle asymmetrical fault current, which is equal to RMS half cycle factor, okay, factor times with the RMS value. Okay, for RMS half cycle factor, this is the formula. Okay, to get the factor. Okay, besides we use this formula, we also can use value from table. Okay, so I will explain how to use the table in the next slide. Okay, next we go to example 8. Okay, the source impedance at a 12.47 kV distribution substation bus is 0.4 plus J 1.5 ohms per phase. Okay, calculate A, the RMS fault current. Okay, B, the maximum peak instantaneous value of fault current, and C, RMS value of half cycle fault current if a balanced 3-phase fault occur. Okay, this is the solution for example number 8. Okay, for A, we have to calculate the line to neutral voltage. Okay, this voltage is in single phase. So V ln is equal to V 3 phase divided by square root 3, which is equal to 7.2 kV. Then we have to calculate the RMS symmetrical fault current. Okay, IRMS is equal to V divided by square root R power of 2 plus X power of 2. Okay, this is the value for IRMS. So this is the Z equation. Okay, next for questions B, okay, we have to calculate the maximum instantaneous peak current value. So to solve this problem, to solve these questions, we first have to find what is the value of instantaneous peak factor. So we refer to this column because instantaneous peak factor. Okay, before we get the value, we have to calculate first what is the XR ratio. This one. So XR ratio. So X is the reactance and R is the resistance of the system. So for these questions, we know that XR ratio is, okay, XR is equal to 3.75 for these questions. So we know that 3.75 is between 3 and 4. Okay, this one. So we can see from the this table. Okay, so 3.75 is in between. Okay, this one 3.75 is in between 3 and 4. Okay, so by using interpolation method, we have to calculate what is the value of instantaneous peak factor for XR ratio 3.75. Okay, after we get the factor, instantaneous peak factor for 3 and 4 XR ratio, so we can calculate the instantaneous peak factor for XR ratio 3.75. So by using the interpolation, okay, this is the formula for interpolation method, we can get the value of X. X here is the instantaneous peak factor for SR ratio 3.75. So after we rearrange the formula, okay, this formula we rearrange, and then we get the value of X. Okay, this is the formula after we rearrange, and then we get the S value is 2.0543. This is the value of instantaneous peak factor for XR ratio 3.75. Okay, after that we have to calculate the maximum peak instantaneous value, okay, of fault current, which is equal to factor times with the IRMS. So we get the IRMS value in the questions example 8A. So the value of IP is equal to 9528 M. Okay, next is question C. Okay, we have to calculate the RMS current for half cycle. Okay, first we have to determine what is the factor for half cycle. So by using the same method, referring to the table, okay, here, but we have to refer to half cycle factor here. So still refer to SR ratio for 3.75. okay, this one, okay, between 3 and 4, but we have to refer to half cycle factor, which is 1.115 for 3 and 1.191 for 4. Okay, then by using interpolation, okay, this one, by using interpolation, we can get the value of the factor is 1.172 for XR ratio 3.75. Okay, after we get the factor, we have to calculate the RMS value. Okay, so RMS for half cycle is equal to factor times with the IRMS, which is equal to this value. Okay, I think that's all for chapter 3 part 2A. Okay, next I will continue with part B.